We present IKLink, a method that enables robot manipulators to track end-effector trajectories with minimal reconfigurations. Many applications require a robotic arm to accurately track reference end-effector trajectories. These applications include welding, polishing, painting, and visual inspection. We call this kind of task end-effector trajectory tracking. Most existing approaches assume that the end-effector trajectory can be tracked using a single and continuous robot motion. However, this assumption can be infeasible for some complex trajectories due to joint limits, singularity, or obstacles elsewhere in the environment. For example, here the robot is stuck because one of the wrist joints is close to its position limit. To track complex trajectories, it often becomes necessary to segment the trajectories into shorter segments. Each segmentation introduces a reconfiguration, where the robot deviates from the reference trajectory, repositions itself in configuration space, and then resumes task execution. Reconfigurations increase energy usage and time to complete a trajectory. Therefore, we present a method that minimizes the occurrence of reconfigurations. Our method takes an end-effector trajectory as input. The trajectory is represented by waypoints. Our method generates multiple continuous joint motion segments that track the reference end-effector trajectory. The robot performs reconfigurations between the segments. Our method involves two phases. The first phase generates a diverse set of inverse kinematic solutions for each point. For example, the two IK solutions move the robot to the same end-effector waypoint. Second phase, we use a dynamic programming algorithm to link the IK solutions to generate motions with minimal reconfiguration. In phase 1, we use a combination of three methods to generate IK solutions. To have a diverse set of IK solutions, we use track IK and uniformly sampling its seeds from the robot's joint space. To generate smooth motions, we use a greedy, optimization-based IK solver called Relaxed IK. One of Relaxed IK's objective is to minimize the movement from a preceding IK solution, so it generates smooth motions. Finally, we use a clustering algorithm, DISCAN, to merge similar IK solutions. After constructing the IK solutions, in phase 2, we first construct a multiple-layer graph where each node is fully connected to all nodes in the previous layer. The edge weights are the number of reconfigurations required to travel between two IK solutions. If the two IK solutions are too far away that the robot can't travel between them within the joint velocity limit, the weight is 1. Otherwise, the weight is 0. With the graph, we run a dynamic programming algorithm to find the shortest path from the first layer to the last layer. The shortest path is robot motions with multiple reconfigurations. The algorithm described in our paper is a little bit more complex because it also has a secondary objective that minimizes joint movement. To showcase the effectiveness of our method, we compare it with two baseline methods in simulation. Our testbed involves randomly generated end-effector trajectories and trajectories to finish welding tasks, close valves, and tighten screws. The two baseline methods use greedy approaches. For details about the baseline approaches, please refer to our paper. Our results show that IKLink consistently finds motions with equal or fewer reconfigurations than the two baseline methods. The results demonstrate the efficacy of IKLink at generating motions with minimal reconfigurations. We also demonstrate the effectiveness of our method on a physical robot. The robot tracks a circular trajectory to weld two metal parts together. Here, the robot is stuck because its pose is close to self-collision. To avoid self-collision, the robot performs a reconfiguration. It deviates from the task trajectory and moves to a configuration that is far away from self-collision. Afterward, it resumes task execution from the new joint configuration and finishes the task. In conclusion, IKLink enables a robot to track end-effector trajectories of any complexity while performing minimal reconfigurations. IKLink eliminates the need to manually segment a long or complex trajectory and is beneficial in scenarios such as welding, sweeping, scanning, painting, and inspection. Thank you for your attention. Please feel free to contact us via email with any questions or comments.